Hello everyone, welcome to this video series on word embeddings used in the natural language processing. We are talking about a particular algorithm called Word2Vec. We have covered quite a bit in terms of intuition, in terms of use cases and examples of Word2Vec. In this particular video, we will be talking about the need to optimize Word2Vec training process. I'll be explaining why we need to optimize the training process and what are those methods or solutions available. And for that purpose, we'll be using Gensim package. Standard word-to-vec procedure is computationally very expensive, especially when we deal with large vocabulary or large data sets. It involves calculating the probability of each word in the vocabulary during the training time, and which can be very computationally heavy, and it can slow down the process of generating the word vectors. So there are a couple of solutions to optimize the training process, and essentially those are called hierarchical softmax and negative sampling. We will be talking about each one of these two methods or solution in separate videos. We'll go into the details and we'll also look at how we set those parameters in the Gensim package. So computational efficiency is important, especially when we talk about large vocabularies. And the optimization methods that we are going to look into, they help reduce the time required to train the Word2Vec model. The optimization methods or solutions are namely hierarchical softmax and negative sampling. So let's spend some time understand what is hierarchical softmax. It is an approach to approximate. So what are we approximating? We are approximating the softmax probabilities for each of the context word. Let's say we are talking about continuous bag of word where the context word is presented and the target word has to be predicted. So in order to predict the target word, we generate the softmax probabilities. With the hierarchical softmax method, we are not going to compute the softmax probability for the entire vocabulary, but only a select few. But the method pretty much approximates the softmax probability as if we are doing the softmax probability for the entire vocabulary. So essentially, it still gives the same or almost the same behavior and results of a true or complete or softmax function. This technique is also applied not just in word-to-vec training or word embedding. It is a general concept. It can be applied in many other applications of neural net, but mostly it is quite popular in the language models. Now, one point to note, without this kind of optimization, it may be almost infeasible or impossible to train a word-to-vec model. And we use softmax, hierarchical softmax in skip-gram models. So the motivation for hierarchical softmax is standard softmax operation requires evaluating the probability for all the classes. Let's say we are talking about W number of classes or W number of the vocabulary words. We need to compute the probability for each of the vocabulary words. And that can be computationally very expensive, especially if the vocabulary size is very large. So hierarchical softmax aims to reduce the computational costs by evaluating the softmax probability of a subset of the vocabulary, not the entire vocabulary, but in order to select the or target the subset of the vocabulary, we have to use another mechanism or additional mechanism in the algorithm, like a binary tree structure. We're going to talk about what kind of binary tree structure we use here. So typical softmax, just like a recap, I'm giving an example here. Let's say MNIST digits, and it's a classification problem, and there are 10 types of digits, 0 to 9, and it goes through the neural net, and the neural net, after the training, is able to detect the digits correctly. Let's say this is for 0, 1, and 7, 8, and 9, and so on and so forth. Essentially, this is about the softmax probability. And we compute the softmax probability by taking the logit of a neuron, let's say this one, and then divide by the sum of the node logits of all the neurons. That's a typical softmax computation. And the result of softmax computation is in terms of probability. And one of the neuron would get the or would be assigned the highest probability. Let's say it is digit 5, then the corresponding to digit 5, the neuron will get the highest probability. That's how the softmax function works, and that's exactly what we do in the case of word vectors also. Now, what are the pieces which are computationally expensive in this softmax computation? One is the exponentiation. If you look at the formula that we use to calculate the softmax probability, exponentiation is a significantly expensive operation. And then we are also summing the denominator. If you look at the formula again, so in the denominator, every time we are summing the logits or the activation value from the neuron here. So these two operations take up significant processing load, and this is what we are trying to address in this particular optimized way of Word2Vec training process. Another problem with the exponentiation is the numerical stability. Higher values can result in error, or it can result in numerical instability during the training process. There is a solution to that also, how we can avoid the numerical instability problem. Let's take a look at the computational complexity in terms of Python demo, and also I'll be showing you the numerical stability as a problem. Here's the little example to illustrate the issues of exponentiation and also numerical stability or instability rather. So just taking some dummy data. So let's say 100 uh, random numbers, and those random numbers are like logits output of a neuron, just for example. And then using the softmax function here, we can compute um, the probabilities. So this is a little function which is very similar to the softmax probabilities, and you call the softmax function using these logits. For each of the value in the logit is going to give you the probability, and one of the values will be the highest here, and some of these values will equate to 1. So the classes that we have here, let's say, we're not starting with 0, but starting with 1, for example. So we just go with 101 because I used 100 neurons here. So let's just plot it here just to visualize the, let's say these are the output or activation values from the neuron, and these are logits here. And the highest value is probably this one is the highest value. And corresponding to this highest value, you have that particular neuron getting the highest probability. So this is the softmax probability computation. So let's take a look at the computational complexity issue. So let's say we have a number of elements, 100,000. That means, let's say the vocabulary size is 100,000, and that's quite large, size. Now, in order to compute the softmax probability, this is the function that we use. What I'm going to do is show you the time it takes to compute the softmax probability for 100,000 words. So the time it takes is 0.12 seconds. Now, in case of Word2Vec, let's say the vocabulary size is 100,000. From that vocabulary size, we are going to generate the training pairs. So how many training pairs? That would depend on the window size. So the training pair is always x and y, so multiply by 2. And let's say the window size is 5 or 3 or 4, whatever. And this is the vocabulary size. So the number of training samples is going to be this equation here, 2 times the number of window size multiplied by the vocabulary. So this is the number of training samples. Now, for these many training samples, we are going to need about 6 seconds to compute the softmax probabilities. And let's say the model runs 10,000 times. So just to compute the softmax computation, you need about 16 hours of time. Now that's only one part of the neural net. There are many other parts in the Word2Vec. You have learning rate multiplication, you have back propagation, you have adjustments to the weights, and so on and so forth. So practically, by using a traditional architecture or of Word2Vec, it is really not possible to train a word embedding model given the size of vocabulary, let's say 500,000 or even let's say 1 million vocabulary words. It is just not possible to do it. Another problem that we face is numerical stability here. So let's take some high values, and then when we compute the exponentiation, this can result in this kind of error, like in an infinity. So in order to avoid this error, we have a little subtraction. So you take the maximum logit and subtract from the current logit, and then you take the exponentiation. That pretty much works. So that means in order for the practical Word2Vec training process, we have to do certain optimization. One optimization is to handle the numerical instability, and the other one is to find a quicker way for computing the softmax probabilities. Yes, so that was a demo on computational complexities and numerical instability problem. Let's get to the main point here, the hierarchical softmax. So number one key point, it is useful when we deal with large vocabulary. Let's say we have a sentence, the majestic mountains and the dense forest create a breathtaking. So we don't know what's the word. So this is where the softmax hierarchy or hierarchical softmax will be useful. Otherwise, we have to compute the softmax probability of all or each of the vocabulary word. And if we have, let's say, 500,000 vocabulary words, so we need to compute for all the 500,000 vocabulary words and then pick the maximum ones. and then you can predict what the likely word here. So in this sentence, when we predict the next word, you have to really compute the softmax probability for all. And this is where the hierarchical softmax is useful. So another example, the scientists studied the behavior of various species. Again, after in the, what would be the likely phrase or likely word here? Again, the same issue and issue of computing the softmax probabilities for all the vocabulary word. The solution is hierarchical softmax. Now, in order to understand the hierarchical softmax, we have to understand the type of tree formation that is used in the Word2Vec algorithm, and that's called Huffman tree. So I'm going to explain with a toy example here what is Huffman tree and how this tree is incorporated as part of the training process. So let's look at the hypothetical dictionary or a corpus. We have the words like TF-IDF 3 times, hot 12 times, Kolkata 7 times, traffic 22, so on and so forth. Let's put them like in this order. Okay, just the order it is, and just we put them in the same sequence. It doesn't matter what sequence. Now, this tree formation is very interesting, and I will tell you the intuition behind this tree. Let's first look at the mechanical aspect of how we form the tree. So what we do first is from this list, we take the tokens, two tokens or the words having the least frequency. So that's going to be TF, IDF, and vector, VEC. Those are the frequencies of 3 and 3. So what we're going to do now, take those two and join them or prepare a tree like this. So you have TF-IDF and then the VEC, which is also frequency of 3, and total frequency is 6. So that's step 1. And we are going to pretty much repeat the same thing till we have formed the entire tree. Intuition of doing so, I will uh, explain after we have built the tree. Next up, so remaining words, just put them just next to it, and then again find the pair of tokens which are having the least frequency. So in this case, it would be Kolkata, frequency of 7, and this is a frequency of 6. So we can put them in a tree. Let's look at how after we have done the second operation. So here Kolkata 7 and 6, we merge them together. So 7 and 6 becomes 13. And this is where your Kolkata and the previously prepared binary tree. Now we're going to repeat again the same thing. Bring the leftover words here. And now again choose the pair of tokens which are the least in frequency. That's 10 and 12, AI and hot. In the next slide, we will put them together and then we form the tree here. So this is 10 and 12. So that's 22 now. Again, we repeat, find out the words or a pair of words which are least in frequency. So if you look at 22, 18, 22, 27, 13. So now in this layer, you have 18 and 22 being the least. So combine, so there are two 22s here. You can arbitrarily take any one of the two. So that becomes 40. Now the remaining out of 22 and 40 and 27, The least is 22 and 27. Join them, and now finally you merge the last pair of you know nodes here, and that's how your tree will look like. Now, what we have gained by this tree, if you look very closely, is the following. The words with lower frequency, they are showing up below, and the words with high frequency, they show up early in the tree. Now, what we're going to do with this tree formation is the algorithm is going to assign the code to each of the word. For example, let's say AI. This word AI here will have the code starting from the root is going to start here. So left and right. So let's say the convention for left is 0 and right is 1. So this is 0. Then again you take a 1, and then again you take a 1 means the right to get to AI. So the binary code or the code or encoding AI would be 0, 1, 1. And likewise, you can see for Kolkata or TF-IDF will follow like, right from beginning 1, 1, 1, 1, and 0. That's the encoding for TF-IDF. Now, how is going to be useful? In the Word2Vec, when we predict, let's say the target word is ML, then the algorithm will just travel the path and come to this point. And in the path of traversal, whichever word it found is the subset. And the algorithm is going to focus only on that subset and compute the softmax probability. So that's the trick that is used in the optimal or optimized Word2Vec training. So how this Huffman tree actually works or hierarchical softmax work in the Word2Vec training. So first we need to build the Huffman tree. That means the Word2Vec algorithm will actually build the tree, Huffman tree, as the first step. Words with the higher frequency are up in the order. Words with the lower frequency will be down the order in the tree. So that means the words which are occurring more number of times, they are easily or quickly accessible than the words which are not very common. After that, the algorithm is going to assign the binary code to the tokens following the convention that we described a couple of slides back. Now, the binary codes are constructed in such a way that the moving to the left is 0 and moving to the right of the tree is 1. So the model, when it incorporates hierarchical softmax, which is actually a configuration parameter. I'm going to show you how you configure that in the Gensim package. So the output layer is essentially the Huffman tree, not the complete vocabulary here. So during the training time, instead of computing the probabilities for all the words in the vocabulary, we are going to use the Huffman tree for the target word and travel down the tree and find that particular word, which is our target word. And during the path of the traversal, whichever word that we encountered, those are the subset of words for which the algorithm is going to compute the probabilities. And that significantly reduces the computational cost. So the training part is for each training pair, The model's objective is to predict the context word based on the target word. If it is skip gram model, let's say the target word is traffic with the code of 1 and 0 in the Huffman tree. So we need to predict now where 1, 0 exists in the Huffman tree. Start with the root, move to the right, then that would be 1 here, and then move to the left because you have 0 here. So you move to the left hand side, and that traversal leads you to the word that we want, or the word which is a target word here. Now, in the path of traversal, we will gather or retrieve the subset, and we are going to perform the gradient descent or gradient or derivative computation only for those words. So the nodes with the binary code 1 and 0 are the ones which are updated, not the other words. So this is the significant reduction in terms of computation time. So what happens in the prediction then? Almost the same thing or exactly the same thing given the input. Let's say the input is AI. We will travel the Huffman tree and let's say one for AI based on the Huffman tree structure. And during the prediction, the model only needs to evaluate the subset of nodes along the traversal path. And then the model computes the probabilities or softmax probability based on the subset of the nodes without the need to compute for the entire vocabulary. I hope this explanation was useful. Next, I'm going to show you how we configure this in Gensim, and also I'm going to show you the code. So the hyperparameter in Gensim is called HS. HS is for hierarchical softmax, and you set that to 0 or 1. So when you set it to 1, hierarchical softmax will be used during the model training. If it is 0, then it is not going to be used. There is another method which is called negative sampling, which also achieves the similar objective of reducing the computational time. That will be the next video. We will talk about what is negative sampling. So you have two methods or two optimization techniques. One is hierarchical softmax and the other one is negative sampling. These two methods are used like an option. So either you choose hierarchical softmax or you choose negative sampling. In the next video, I'm going to explain what is negative sampling with example. Then after that, I'm going to show you the advantage of training without hierarchical or negative sampling, and with hierarchical and negative sampling, we'll see the performance difference. Thank you all. We'll see you in the next video.